Well, hello everybody, and welcome to this FIB webinar introducing you to Bulletin 101, Precast Concrete in Tall Buildings. My name is George Jones and I am convener of Task Group 6.7 in FIB that was responsible for the production of Bulletin 101. The Bulletin 101, Precast Concrete in Tall Buildings, was produced in collaboration with and also published by PCI. This webinar seeks to introduce you to that bulletin, and we have put together a webinar that includes 4 presentations that we hope will give you a taster for what's in the bulletin itself. As I said, my name is George Jones. I was the convener. And I will run through the background to the bulletin and its content. I will then be followed by Dick van Keulen, who will give you an overview of precast concrete framing systems. And thereafter, Mischa Falger. Mischa will discuss the links between design and achieving benefits in construction of tall buildings in precast concrete. And finally, Stefano, Pampanin, and not least, of course, who will discuss the developments in precast design in seismic areas and give you a taster for how precast concrete could become the preferred structural form in seismic zones. We will then have a short question and answer period where we, all 4 of us, will be available to answer any questions you may have. So going to the background of Bulletin 101 and why FIB Commission 6 thought it would be a good idea to produce a bulletin of this type. There is great current popularity in tall buildings. This has probably been the case for the past couple of decades, I would say, and several references have been written on their design in both steelwork and structural concrete, including FIB Bulletin 73, which is named Tall Buildings and was published in 2014. This bulletin covers all buildings in concrete, so is not specifically for cast in place or for precast, but FIB Commission 6 felt that a reference specifically for precast concrete in tall buildings was overdue. On that basis, in 2014, Commission 6 formed Task Group 6.7. We had 32 members, and those members were spread globally from 16 countries. And its aim was to bring together in a single document an up-to-date reference for the modern applications of precast concrete in tall building construction. After 4 or 5 years, the finalized draft became available in 2019, and this was towards the end of 2019. So unfortunately, the finalized draft coincided with the start of the COVID-19 pandemic. There was a resultant slowdown in the final lap, so to speak, of the completion of the document, but with a lot of perseverance, it was eventually approved by both FIB and PCI in 2021 and published towards the end of that year, and is now available from FIB for purchase. So this is the finished document. We have 12 chapters in the document. And the bulletin, we decided at a very early stage to divide into 4 parts. The first 4 chapters discuss how benefits can be achieved with precast concrete and how precast concrete can be integrated into any tall building. Chapters 5 to 8 then cover the individual building blocks, as we'd like to call them, in precast concrete, which would mainly be floors, columns, walls, and stairs. And particular attention in these chapters was paid to design and detailing of the elements and the production methodology associated with each of them. There was particular attention to connections in this area, which is often one of the things that people ask about in relation to tall buildings and precast concrete. In chapters 9, 10, and 11, we then looked at areas of specific interest, and those areas that we chose were building facades, precast in seismic zones, and construction of precast concrete in tall buildings. And finally, we finished with 15 case studies, and we tried to draw examples from throughout the world, and we have examples from Europe, North and South America, Australia, Japan, the Middle East, and China. So going back to the various chapters in the building, chapter 1, we looked at the characteristics of tall buildings. They generally have a small footprint due to the high land values where they're built and the restricted space available. They tend to have a repetitive layout above the lower levels, giving rise to repetition of form and so on. There is an increase in the relative magnitude of lateral loading due to the tallness of the building compared to gravity loads. And there is great importance in vertical service cores for purposes of structural stability, not only for the cores themselves, but the structural stability that lends to the building, and as a fire escape, which is extremely important in tall building design. So just looking at examples of small footprint and repetitive arrangements and service cores, I've chosen 2 examples here. You can see on the left, this would be typically an office building with a proportionally large service area with stair cores, lift shafts, service risers, etc., and a range of perimeter columns and open space in between the service core and the columns and the perimeter of the building. On the right-hand side, you can see a typical arrangement of a residential type building where areas that are accommodated by walls and so on can be used as part of the structure. So with tall buildings, there tends to be a cost premium due to the tallness of that building. If you look at the very simplistic graph on the right-hand side, the solid line indicates an optimum design where the design relates to resistance to gravity loads only. The broken line is the line that indicates what would happen in a tall building relative to just designing for gravity loads. And you can see there's a premium there. As the building gets higher, the cost of structure per unit area begins to increase. This gives engineers a challenge in that they need to then develop efficient and innovative structural systems that minimize this cost premium, but also satisfies the building's performance requirements. Now, what are these essential components? Well, each tall building requires its cores, which take up a large proportion of the floor area and include stairs and landings. They also have floors. They also have other vertical components supporting those floors, columns and walls, and they also have a facade. These are essential components in buildings of this type, and all these components can be provided in precast concrete. So a solution can be delivered in precast concrete where the structural frame is part of the functional building. That is, there's no separate frame required as you would have in a steel building where the other components are supported by a separate steel frame. The building, the functional parts of the building act as the frame. Chapter 2 of the bulletin looks at benefits of precast concrete in tall buildings. And we all know that there are great benefits in concrete itself, whether it's precast concrete or in situ cast in place concrete. It has high quality and low maintenance, great fire resistance, strength, temperature control and insulation, acoustic separation, durability, visual flexibility and sustainability. We all know of these properties. However, in precast concrete, there are extra benefits that can be achieved. These benefits are reduction in floor cycle time. I expect Mischa might talk about that later, where floor cycle time becomes critical in tall building construction. And this is the time taken to construct a single floor and supporting vertical elements. The increased time certainty and improved completion dates. Again, weather, climatic effects, and so on, don't affect precast concrete, which is made off-site. There's less congestion at the job site because the concrete is made off-site. Then all you need are a few people to erect the concrete and complete the connections. We should have budget certainty and value for money because the precast concrete is not generally affected by site-based risks. There should be quality certainty as elements are produced in advance of construction. So elements can be inspected and it can be ensured that the quality required in the building is achieved at the factory and not left to be inspected on site after removal of shutters and so on. And complex components can be made off-site, and often there are relatively inaccessible locations at high levels that cause difficulties in cast-in-place concrete. So chapter 3 then looks at integration of precast concrete into mixed construction. We have several combinations there. I won't run through all of them. That list will be available on the video on YouTube, but precast concrete can be mixed with other elements of in situ concrete, often the central cores, or with steel frames. In chapter 4, we have precast concrete structural systems. Dick van Keulen will be talking about this in more detail in the next presentation, but generally these can be split into 3 areas: frame systems, shear wall systems, and tube systems. In chapters 5 to 8, we have our building blocks, and you can see some examples of the types of components that can be used in precast concrete, from floors to walls to columns and stairs and landings inside service cores. In our special topics, we look at facades and cladding, precast seismic zones, and construction. And finally, in chapter 12, we have our case studies. There are 15 case studies. You can see from the list there, they come from throughout the world. Each case study looks at a different use of precast. So just running through them quickly, the Bella Sky Hotel in Denmark was a full precast frame, was an award-winning building. The Dexia Tower in Belgium was a mixed construction of precast columns and floors with in situ cores. Breaker Tower in Bahrain was a full precast frame. The 2 Japanese examples there were full precast frames in seismic zones. The Tampa Tower in Finland was a precast facade matching its surroundings. The Brazilian example was a multi-story frame basement that in the end supported a steel tall building. The Conjunto Paragon, Mexico, is an award-winning precast facade. Again, in the USA, another precast facade at the Northwestern Memorial Hospital. The Erasmus Medical Center in the Netherlands was a full precast frame with a novel way of constructing that frame, which Mischa will discuss later. The Paramount in the USA, a full precast frame in a seismic zone using post-tension technology with precast elements. The Premier Tower in Australia, a very tall building using precast vertical elements in mixed construction. Similarly, Australia 108 in Melbourne. A seismic resistance office structure in China that was a full precast frame in a seismic zone. And finally, the Torre de Cristal in Spain, which was a mixed in situ concrete and steel frame, but using precast hollow core slabs throughout its height. So that gives you an introduction and hopefully a flavour for the bulletin itself. We now have 3 specialist presentations, and I would like to hand over to Dick from Keulen, who will talk you through precast concrete frame systems. Thank you.
Thank you, George, for introducing me. My name is Dick van Keulen. I'm from the Netherlands. I'm the founder of an engineering office, and we are specialized in design and engineering of precast concrete building structures. Apart from that, I'm doing research at Delft University in the field of precast concrete. I would like to start with the view from my office over the city Rotterdam. And in this is the so-called the capital high-rise city of the Netherlands. The buildings are not very tall compared to other cities, but it's nice to see buildings that are constructed with the precast concrete construction method. At the left, you see the Erasmus Medical Center with a tallness of 120 meters. And this building is also in the Bulletin as a case study. In the middle one, you see the Zalmhaven Tower, which is supposed to be the tallest precast concrete building at the moment. And the third one is the Delft Support, also 150 meters. And I selected these 3 towers because they were constructed with a hoisting shed instead of traditional tower cranes. And that's nice to see. Then the content of my presentation, I'm asked to present on structural systems. And then we need also to say something about precast concrete element layouts in combination with connections. And finally, I will present you the breaker tower as a case study, which is also included in the VIP bulletin. This is a known chart for concrete buildings. It's a very simple chart. It links the structural systems to a number of stories. So you see here a framed structure, and according to this chart, it is able to resist loads from for a building up to 20 stories. And on the right side, you see the tube structure that is able to resist loads on buildings for 65-meter high buildings. When we go into the structural systems, a very well-known one is the shear wall, and it's a 2D structure, and that can be composed of precast concrete large panel elements. An alternative on shear walls is the coupled shear walls. In fact, that are 2 shear walls, and they are connected with lintels between the shear walls. And there is a structural cooperation between both, and that increases the capacity of the shear wall. When we look at tall buildings, then we have a mixed type of structures, and that are 3D structures. For example, a core with the elevators and stairs, but also the facade is able to be part of the structural system. Here you see a framed tube structure. It has openings, and it is a frame structure is able to resist, to transfer the forces to the foundation of the tall building. Each structural system needs a precast concrete element layout. And when we start with the shear walls, you see on the left a interlocking element layout. And all these individual precast concrete elements are interlocked with one another with the goal of getting a shear wall functioning for transferring all vertical and horizontal loads to the foundation. An alternative for interlocking elements is the one next to it without interlocking. And the benefit of this type is that the shear wall can be constructed with less elements. If you go to the cores in the middle of the sheet, yeah, most of the time there are door openings present, and they need to be incorporated in the element layout that should be chosen for the core, the concrete core of a precast concrete building. At the right side, you've got the tube and tube structure. In the center, you see the core, which can be precast concrete, but in a mixed structure that can be in situ concrete as well. And the facade of this building has an element layout for precast concrete elements. The wall elements need to cooperate with each other, and therefore connections are needed to transfer the shear forces from one to the other element. That is required in vertical connection, but also in horizontal connections. At the right side, you see the bending moments, and bending moments includes compression and tensile stresses, which have to be taken by the horizontal connections. This is the well-known mortar connection. It's a filling of a horizontal seam, and it has vertical steel bars. Such a connection is able to transfer shear forces, but also compression and tensile forces throughout the shear wall or other type of structure. In case you need more shear capacity for this connection, then it's possible to add shear keys to the interface, which is visualized in the photo on the right of the sheet. Typical vertical connections are displayed in the sheet. On the right side, indeed, that's the interlocking core bell that can be applied in a corner connection, but also when two walls are positioned in a line. The third one is in C is a welded connection. But when we speak about tall buildings, most of the structures are constructed with cast in place loop connections. And this is an example of a cast in place loop connection. The upper one is a traditional one. There are hairpins added through the edge formwork and in the concrete factory. And at the construction site, the space between the two precast concrete elements will be filled with cast in place concrete. And to do that, you need formwork to keep the concrete in place. The reband connection is an alternative on this. This is more precast friendly, but this is that function as the same as the cast in place loop connection. This, in fact, is an alternative. Again, when you need additional shear capacity for this connection, it's possible to add shear keys in the interface between the precast concrete and the cast in place concrete. So this is quite often applied in precast concrete tall buildings. when we go to the functioning of vertical connections, I would like to start with the third picture, where in fact the vertical, which are in fact three individual shear walls clamped into the foundation without connections, and that indicates the K is 0 and K is the shear stiffness. So there is no connection between the three walls. And on the other hand, when we have a shear stiffness, when it is infinite, then we have the monolithic concrete structure, and that one is depicted on the left side. And the precast concrete shear wall structure is depicted in the middle. And then the shear stiffness of the connections are in between the infinite shear stiffness and the stiffness without of a shear wall without connections. And this has to do with the displacement, which are very important for tall buildings. But what we have as well is the force distribution. And what we see is that the precast concrete vertical connection weaken the shear wall a little bit. But the force distribution changes also a little bit, and the structural engineer has to cover this. And you see here on the left side the monolithic shear wall structure with shear stresses and with vertical stresses from bending. And you see in the middle the precast concrete alternative with vertical connections, and you see that the shear stresses and the vertical stresses are slightly changed, and that should be incorporated in the design of the shear wall structure. Now, this is also the case for framed structures, whether it's a 2D frame structure or a 3D frame structure. Then you see also that the force distribution changed and the displacements at the top of the building increased a little bit. I was also asked to present the breaker tower in Bahrain. This is the second part of my presentation. This is a 165 meter high precast concrete building. It was completed in 2015, and at that moment it was the tallest fully precast concrete building in the world. This building at the ground floor there is a showroom accommodated. On top of that there is a parking garage, and in the high-rise part of the building there are apartments and penthouses. And as you can see in the plan of the apartments, the apartments have a very open space, so you have a good outlook to the surroundings. And yeah, the backbone structurally of the tower is situated at the left, at the back of the building. This building has 35 stories, and that's not a lot for such a high building, but that's because of the 4.2 meter free story height, which is part of the luxurious environment over there. They give the resident a lot of space. Then I would like to go into the precast concrete components of this building. The open at the front side there's an open structure with columns, and between the columns there are invited T-beams placed, and they used hollow core slabs plates for making the slab, and they are placed on the T-beams and also on the walls. What you can see is the round circle here is that that was difficult to make that with hollow core floor, and they choose to apply in cast in situ round shaped cast in place slab. That's what they make there to make the apartments with an overview. On the left side, you see all the walls, and that are shear walls. They are all shear walls. They are coupled together. Here are some pictures of this building. In the left one, you see the shear wall at one side of the building. This is the back wall of the building. Here are 4 precast concrete elements connected per floor, connected to one another. They make inner spaces where they put in precast cast in place concrete in order to connect the 4 wall elements together so that they form the entire shear wall structure. When we go into the details, that's I think very interesting, because they designed a connection where no traditional formwork is needed. So that's because of the inner space. That's very precast friendly. They applied vertical hairpins, as you can see on the photo. And they do that because when the precast concrete element is hoisted by the crane, you have to move it vertically, and horizontal hairpins would cross one another, and that's not possible. In the connection, they make share keys, but also, as you can see in the middle wall, and on the right side, you see there that they add a roughened interface between the cast in place concrete and the precast concrete, and there they were able to transfer more shear forces from one element to the other. It's also important to have a solid diaphragm action. What you can see here is that over the precast concrete wall, there is a cast in situ space where they make the tying reinforcement, and that is that's available on top of every precast concrete wall element, and that together they form a very solid, stiff in plane slab. Then a few words about construction. The construction took 1 story per 13 days. Of course, they start with more days per floor, per story, but at the end they did it very fast, and they needed the largest tower crane of the region. So this was my presentation. Thank you for your attention, and I would like to hand it over to Mischa Falger.
Thank you, Dick, for your introduction into the way of constructing and aspects with that. I'm talking about actual construction of the buildings from a constructor's or contractor's point of view. My aim is, in the limited time I have, to give the audience a little taste of how a contractor looks at a tall precast building. After introducing myself and the company I work for, I also would like to make a link between how you construct a building and what impact that has on the design. And of course, I would like to tell you a little bit more about some of the projects. In fact, all 3 buildings Dick showed in his first slide are in Rotterdam and are built by the company I work for, which is BAM. BAM is the Netherlands' largest contractor, and also has a strong presence in wider Europe. We are doing projects in 6 or 7 countries on a regular basis, and we are involved not only in building buildings but also in infrastructure and everything which you would expect from a big construction company. As a person, I'm a structural engineer by education, and I've worked most of my career for BAM as a contractor, but with a structural mindset. And what we try to do in our office is to come up with smart solutions and optimize designs so that BAM is enabled to build those buildings efficiently, and therefore is competitive with other colleague contractors. When a contractor looks at precast tall buildings, a few things come to mind. Of course, safety. Safety is something which is very important to a construction company. Of course, in the precast tall buildings, precast is an important part. The fact that the building is tall is an important thing. Logistics is always something to think about, and time on most projects I've been working in my career is of the essence. So I'll try to go into those 5 aspects into a little bit more detail. Safety is paramount, as I said before, and safety is looked at from different angles. It's first of all, of course, personnel. You want people to work on a safe environment. You want your personnel to go home every day after a day's work on the building site, but also the surroundings are quite important. Falling objects is something we worry about a lot. If you are moving materials using cranes and something would fall from a crane, typically high-rise buildings are in a very built environment with lots of streets and other people walking around. So you would like to keep everyone around your building site as safe as possible. The picture shows some safety zones around buildings. The blue one is part of the project, which is less tall. The red one is the increase of safety area you need around tall buildings. So the fact that a building is tall has implications for safety and the way we look at that. Well, George gave a good example and a good list of things why precast is an interesting way of building buildings. As a company, we like precast for several reasons. The quality, as mentioned, is a big part in that wish to build precast. And if we do so, we are focused on things like element size and weight, the way connections are designed and need to be applied in the building, and of course also transport of elements and the way it is positioned in the building. Typically, you need to take all those factors into account to come up with a solution which is actually buildable. I will make a reference to that later on in the design part. But all those aspects of precast are very important to a contractor, because the combination of those factors actually make a project work or not. And I think that is an important thing to remember when you are a designer. Many times we come across buildings which which are very suitable for precast construction with all the benefits that come with that, but are designed as an in situ concrete building. And to make that step, especially for a tall building, between in situ into precast is a big leap, and something a designer really should be focused on. Well, tall has, especially for a contractor, has big implications. For instance, wind speeds increase with height. The figure on the right is maybe not completely readable, but the essence of that is that wind speeds above 11 meters per second are difficult to handle for cranes, and basically mean that you can't use your crane for that day. Well, if you look at the number of days which are expected, at least in our country, to have wind speeds over 11 meters per second at a building height of 50 meters, that is just under 7 days a year. But if you build a building of 200 meters in the same spot, that number of days increases to almost 38, which has a big impact on your time schedule in the overall things of the construction. And that basically also goes for the vertical time you need to transport your elements. You can imagine that if you pick up an element and you only have to transport it up for 20 meters, that is a different thing than do that over 200 meters. So that is, from the perspective of tallness, an important factor in the contractor's mind. And also the accessibility of the facade is something very important. If you build a building of 20 or 30 meters, you can put up some scaffolding around the building, but as soon as buildings go above that number, it is difficult to access the facade from the outside. So that is also something we are especially interested in when looking at buildings to construct. From a logistics point of view, high-rise buildings are often located in the city centers of big cities, which almost by definition means that you have a very small building plot, that the access to the building site is limited, and that all the work you have to do, building a very tall building, has to be crammed into a small area. This particularly is of interest to a contractor because that actually means that you have to organize your building sequence and all that sort of things in a completely different way than when you would when you can build the same volume of building over a spread out area. So from that point of view, the fact that the building is tall and always in the city center is something to keep in mind. And George already mentioned cycle time. The time you need to complete one floor is something which is very important to a contractor, because once you get into a rhythm of precast, you need to make that cycle every week to keep up with the time schedule of the total project. Well, if you have a building which is tall compared to a regular size building, this vertical transport is getting a big impact on your cycle time. Typically, we try to get a floor done every week. That is something which suits our company and our suppliers and the way of thinking in our country. But you can imagine that if you have to transport an element, let's say a facade element, in a vertical way, using cranes, this takes about 5 minutes up and down for a building which is 50 meters tall. But as soon as you get to the 200-meter limit, you need, for the same element, you need almost 20 minutes to get it up. Well, that is something which is of significance on this cycle time. So one of the solutions there, from a contractor point of view, we use is to try and minimize that vertical transport, in the sense that we try to get as much material up in one go to minimize the number of times you have to go up and down. And practically, this means that we try to maximize the element size, to use the maximum element size, and that is limited by the road limits to which you can transport that element, which in our country is somewhere between 35 and 40 tons per element. I will get back to that in a little while. Coupling those issues to what you can do or need to take care of when you are designing a building is that element size and weight actually matter. If you are trying to maximize your weight so that you minimize the number of vertical movement, it means that you have to adjust the element size, because at the bottom of a high-rise building, the wall thickness typically is thicker than when you go to the top, which means that the other dimensions of the element at the bottom stories need to be smaller, since you have a fixed weight limit. That is something which has impact on the structural behavior of your building, as Dick illustrated. So from a design point of view, this is something to take into account. Also, the connections, wet or dry, are very important. Stiffness is a key factor in designing a tall building. And from a contracting point of view, we have preferences for certain type of connections, because some of them are easier to make than others. Take, for instance, welded connections. Typically, because of the internal finish of the building, the designer would like to make those connections on the outside of the structural elements. Well, try and do that with a welding equipment at 150-meter height on the outside of the building. That is really something we are looking at. So connections and the way they are made and positions in the building are of significance for the construction sequence. And that also goes for the elements. In the case study, I will show you a way of constructing those high-rise buildings where there is no room to change the sequencing of the elements. That means that for every floor, the order in which the elements are put in place is fixed, and that has impact on detailing, because it's sometimes not possible to connect element B to A if you have designed for connecting A to B, and that is something to take into account from a design point of as well. So one of my jobs within the company is to take a precast design and take all these aspects into account, and then check whether the basic and the overall design of the building actually still is what it is after we've tried to come up with a buildable precast design. Well, there's different ways of building or erect precast buildings. If you have a large building plot, typically crawler cranes are used. Although crawler cranes can reach great heights, as shown is shown on the right, types of these cranes are not really practical on a high-rise building site, simply because of the fact that they are quite bulky and not to mention very expensive to rent. So for tall building constructions, this type of crane is not ideal. That's exactly the reason why in most tall building sites you find tower cranes in all sorts and sizes. Typically, one crane is used to do several things. The elements have to be transported vertically, so from ground floor level to the level where they have to be installed. But the crane is also used to do horizontal transport of that element across the building site, and also used to position the element. If you combine that with long time spent to actually get the element up, and also take into account the fact that the element has to be connected to the crane until it is fully positioned and stable by other temporary structures, it could mean that you need half an hour to 45 minutes on the crane with just one element to get it from ground floor level into the final place in the building. Not to mention the fact that if you would like to position a 40-ton element at a distance of 25 meters, you need huge cranes to actually do that, because of the high impact of that load. So, in a sense, constructing tall buildings from precast elements, the use of tower cranes, although used very much, is not ideal. So that is why in the last years we've come up with a separate and a different way of erecting these kinds of buildings. All three buildings Dick showed you in the past sheet are erected by using a self-climbing assembly hall. Basically, this is well, it's not a factory because the elements are made off-site and transported to the site, but this hall is actually put on top of the building to erect all the elements there. In the bulletin, there's a case study about the Erasmus Medical Center, which is a 100-meter office tower with a prismatic floor plan, and I think that's important to be able to use this type of construction method. The building was completed in 2016. And by using this self-climbing assembly hall, we were able to disconnect the vertical transport from the horizontal transport on the site and positioning of the element, which means that by using two separate cranes for that. These two are independent, and you only need one crane to get all the material up into the building, and you use the other one for positioning and transporting horizontally. And this usually decreases the impact of the height of the building. The cycle time can be the same as long as your vertical crane is able to get all the elements you need up there as fast as needed. The elements and the use of cranes is much less impacted by wind because they are confined within this assembly hall. On most sites, it's possible, for instance, to locate your vertical crane on the side of the building which is least impacted by wind. So this reduces those 38 days of unworkable weather because of wind to what is usually standard to 5 or 10 days a year, which is important. And last but not least, by making an enclosed environment for people and personnel, it's much safer to work in. It's a clean environment, and also the hazard of falling objects is minimized because everything is confined within this assembly hall. What we did for Erasmus, we have used later on for the Zalmhaven Tower, which at my knowledge is the currently tallest fully precast building in the world. It's recently completed late last year. And since this is the last and updated version of the Erasmus principle, I thought it would be nice to show this to you. The Zalmhaven Tower in Rotterdam is a 250-meter residential tower with in total 62 floors. The bottom part is a commercial podium and is cast in situ. That's the bottom 6 floors. And from a constructing perspective, that is for several reasons. Typically, the podium is different from the floors above. So there are shear walls, transfer walls, there's different story heights, there's strange openings, just simply because the use of that commercial podium is different from the residential part. And therefore it's impractical to do that in precast elements because you need a lot of different elements. And by making this part in situ, you also buy time to start producing the elements you need on the higher floors, because once this self-climbing assembly hall is going at 1 floor per week, you need more elements than the factories can produce in 1 week time. So they need a head start to start producing the elements, so that once you start using your assembly hall, they can keep up with the demand. Well, this building has a standard floor plan, which is square. Indicated are the green lines, which are internal walls, and the red lines are parts of the facade, which are actually load bearing and also part of the structural system. In basis, every element in this building is made from precast concrete, except for an in situ floor topping. And the reason for that is that in our country, the Netherlands, it's quite common to put all surfaces for apartment buildings in floor. So all the air ducts, all the wastewater treatment, all that sort of installations is in the floor. And it's very impractical and almost impossible to do that at this scale in a fully precast element. And also because it's a very tall tower, there are special requirements for robustness, which are easily met or more easily met by putting on an in situ topping. So basically, half of the floor thickness is precast, and the top half is cast in situ. And to enable the walls to work together as a one structural system, we have different types of connections between internal walls and between the walls and the facades. All those connections are wet and are of the type as described by Dick earlier. But from a construction point of view, it's something we spend a lot of time to actually get that right and to get that into the sequence in a correct way. Well, the end of my presentation is to show you a little bit of what this self-climbing assembly hall actually is. Basically, it's a big factory on top of the building. In that factory hall, there's two big gantry cranes, one for getting the elements from street level up to the level you're constructing, and the other one is for picking up that element and transport it horizontally and position it at the right position in the building. If you look at this plan, there's a big hole in the assembly hall which enables the elements to come up. There's a position in the middle, which is a position where we can store elements that are to be placed later on. The whole factory has also containers and amenities and all that sort of things for the people working in this hall, so that they don't have to go down during the working day. In itself, it's almost a factory when you look at it. This is a picture looking a little bit down into the hole which receives the elements from ground floor level, and on the right you can see that it almost looks like a normal factory where precast elements are made. And what you can also see is that the elements, the facade elements of the floor that is being just finished, they are completely finished. So the facade elements arrive at the building level complete with insulation, with cladding on the outside, with glazing. The only thing we have to do is to put them in place and grout the bottom, and then that outside area of the building is also ready. So within this 1 week of cycle time, we actually complete the floor, the structural elements, but also the facade. Another look inside the factory, and since I can imagine that it's difficult for everyone to understand how this actually works. I've tried to show that in this picture. Basically, this factory is on 4 tall legs, starting at ground floor level and supporting the weight of the assembly hall, including the cranes, for the duration of the project. Of course, this needs buckling restraints and to keep those legs close to the building. Things like this are designed. Those are stacked at the top of the assembly hall and are put in place every 6 or 7 floors to keep those legs straight while using. And since pictures can say more than words, I would like to end this presentation with 2 time-lapse videos. The first one is about jacking the system, because every floor you have to push up your assembly hall with 1 floor, and that is done at ground floor level, so that everything is at an easy accessible point. And the second time-lapse video actually shows 1 week cycle of constructing the 1 floor. Once the system has been pushed up 1 entire floor, the wide legs are supported by the blue support structure. The jacks go down, and we insert a new wide element, a new tube, and then you can do the whole exercise again for the next floor. And well, this time lapse gives you an idea of 1 cycle, how we complete 1 floor. In total, 82 concrete elements are installed within that 1 week, 5 days of work of an average of 10 hours per day. You can see the elements come up on the left-hand side of this picture. They are positioned in the storage area until the second crane can lift them up and position them in the right position. You can also imagine that it's impossible here to switch that sequence, because there's no room to actually take elements across other elements which are already in place. And in this way, in 42 months, we have constructed the tallest precast building in the world currently. thank you for listening to me. And Stefano, I would like to hand over to you to say something more about the seismic aspects of tall buildings.
Thank you, Mischa. First of all, welcome everybody. And thanks to the FIB to organize the webinar. The work has been an amazing work, and I should credit most of all George Jones, who not only led a dynamic committee, but more than that, was really taking an amazing leadership in authoring, editing, and pushing the bulletin out, which is a very important document. You will not, I saw the questions, you will not learn or become an expert in precast concrete by reading a few hundred pages, but you can use that as a background document to go to different other references, including many of the FIB, and there is plenty of very useful material the FIB as well as other Learn Society are producing. So I will try to give a roadmap in the topic of seismic design of precast concrete tall buildings. On the left-hand side, you see a 39-story building using post-tension technologies, the press technologies, the tallest building using that type of technology in San Francisco, is one of the case study building adopted in the appendix of the bulletin. And the idea is to discuss about safety, seismic not only, but generally speaking, safety, resilience, and sustainability. Is not only about speed, is not only about quality control, but is much more than precast, especially when used in seismic design, can deliver. And today, resilience is a terminology which is much more adopted. You can see here a curve of resiliency. This is a typical trend of an impact, which can be caused by an earthquake, can be caused by a hurricane, can be caused by a catastrophic event. But generally speaking, let's say an earthquake, you're going to receive a reduction of performance, of functionality. And then in the time, the x-axis is the time, you're going to recover. And it's going to take a while. The area of that taking a while is going to be a measure of how much not the resilient you are, or in another way, the lower the area, the more resilient you are. Also, life cycle analysis coming into place. The Green Deal in Europe is discussing about sustainability, and we are working specifically to confirm an idea, which is earthquake damage due to occur with a probability of occurrence in the lifetime of events is going to cause not only cost of repairing, not only downtime, not only obviously life safety issues in a way, but also a sustainability demand, which means from a social, economical, and environmental point of view, you're going to have an impact from a sustainability point of view, and that can be calculated. Just to mention a practical parameter that you can calculate is the not only cost of repairing, but is the energy required to repair a building after an earthquake. The energy as well as the carbon dioxide that you're going to use and push out in the environment, because you need to use more material and you need to repair the building, is going to be a concern from a sustainability point of view. So that's the idea of the overall picture. And then I will finish off with an example of a case study building where we are showing the seismic behavior and the benefits from the point of view of cost life cycle analysis wise, from the point of view of reducing the repairing cost of a building. Fast and quick, we have an international problem, and I was very pleased to see people waving, saying cheers from different countries in the chat. We have people from South America over here. We have actually 160 registrants, we've been told. Only 73 are apparently in presence, but 160 were registered, and they are coming from different countries in the world. We have people from New Zealand right now connected. We have people from India. We have people from, obviously, from Europe, and many other people. I saw someone from Cambodia and so forth. So there is a problem, which is an international problem. And if we go back to the 1990s, precast was not well seen. Precast was in the use of in seismic zone was limited due to lack of confidence on the performance. In 1994, there was an earthquake in Northridge in California, 1995 in Kobe in Japan, 1999 in Izmit, Kocaeli, Turkey, and precast behaved according to the detailing. I will be using this terminology so much, detailing. It's not a problem of the material, it's a problem of connection design, is a problem of conceptual design, and generally speaking, is a problem of lack of rational seismic design provisions. You do not have a code. You don't learn precast and pre-stress and post-tensioning at school, at university, so you are in trouble. So in the 1990s, precast in seismic region was adopted, but with quite major restrictions. The restrictions were, you could use an emulation or cast-in-place approach, the famous wet connections, or you could use strong connection, provided that the inelastic demand due to the earthquake was not accommodated within the connection between precast elements. The novelty became, after the 90s, this jointed, dry, ductile connection. That's what we want to discuss about in these very few minutes. It's not anymore an issue of life safety. If we're thinking about seismic design, we are obviously targeting life safety, but it's not enough. If you take an industrial building, the cost of the contents, the Parmesan cheese in Italy in 2012, damaged by the earthquake in some industrial plants, were much more expensive than few times the skeleton of the building. Obviously, if you get a full collapse, we're talking about a different issue, but we should be able to design for no collapse or low probability of collapse and life safety. The interruption yet, or though, of the production of such a 24/7 plants, industrial plants, is going to be in few weeks much more expensive than the whole structure itself. So we need to change the gear. What are the key parameters or key aspects in seismic design of precast? They're not that different from other structural materials, but they are more important because you don't have the opportunity to go on site and fix. But this lack of opportunity to go on site and fix is actually what George was very properly saying, is a benefit, is a lack of surprises, let's say in a different way, lack of risk on site, because things should go as right as they can, from a quality controlled manufacturing to a delivering on site to the erections. And Mischa was showing how extremely high technology can be adopted to develop the full system. So we need a conceptual design. We need to discuss very properly what is the lateral resistance system. Sorry for there's a type over here. We need then to think about the design methodology, force-based versus displacement-based. I can tell you right away, it's time, even for very tall buildings, to consider seriously to use displacement-based design, possibly in combination with force-based design. But we need, first of all, to limit the drift. We need, first of all, to limit the displacement. And it's much easier if we start from the beginning from a displacement-based design point of view, even in a low seismic region, or even in a wind-governed type of design. We have to understand the overall building behavior, which means structural system diaphragm, no structural elements, foundation, or the whole building blocks that you will find in the bulletin, is going to discuss about issue or systems, but we need to make it work properly all together, which means displacement compatibility. The stairs, precast stairs, needs to be able to slide as part of a isolated component, like in a base isolated building. The diaphragm needs to do a proper job. The taller you are, the more higher modes you're going to introduce. So you need to be very careful in designing and detailing, here it is, detailing the connections between elements and the connection between the skeleton and the non-structural system. Redundancy and robustness is extremely important. With the same care that we think about preventing progressive collapse during construction, we should be preventing progressive collapse in the seismic response, so in the seismic zone during an earthquake, in the aftermath of an earthquake. So it's very important that it's fundamental that the structural designer will consider redundancy from the beginning and robustness from the beginning of the design. Incompatibility of displacement, someone doing something, someone else doing something else. Think about a tube-on-tube, a dual system, walls, core walls and frames, a dual system, core walls and outrigger, or let's say an outer walls, or core walls and outrigger, using tension and compression to try to give you more balance. The whole incompatibility of deformation between one system and the other, between the floor and the diaphragm, floor diaphragm and the lateral resistance system must be taken into account. Last but first, detailing. Devil is in the detail. In any structural design, we should not forget that detailing is going to be the one saving the building, especially when we're thinking about seismic design. It's not the colorful type of output that you get from your computer model. So let's use the computer model as an assistant, but the conceptual design is the one that is from the first beginning is going to drive the proper design into the proper direction, and detailing is the one that is going to confirm the proper conceptual design in terms of behavior. Our computer model should be a verification. So the idea of, you see here, I didn't put design methodology first. You don't get started with try and see. So it's not a design by analysis, but it's a design as a conceptual design, and then the verification comes with the analysis. We will not be talking about this type of buildings. There is a prejudice. People think that precast concrete is, especially in Europe, we think, the precast concrete is for industrial buildings with this sort of a strange connection, simply supported beams on columns, with big corbels, maybe a couple of dowels, socket foundation at the base, and everything which is very far away from a moment-resisting connection. If we are talking about this precast construction around, not the world, but just going northern in Europe, central north of Europe, you saw what is actually precast concrete capable of doing, and is far away from simply supported or hinge type of connection. We do need, for seismic design, moment-resisting connection. So in the past, moment-resisting connection, and in the present, is well developed using wet connection. You have semi-precast elements which are going to be connected in a monolithic emulative way by casting the wet connection. You can have cruciform joints, you can have T-shaped joints, you can have shell beams, and you can find more information on the FIB Bulletin 78, which has been led by a great engineer and academic and friend of all of us, Spiros Tsoukantas, who is not with us anymore, passionate about precast. He pushed very hard for this bulletin to be able to be completed. And you can find there some basics of step-up construction, of emulative approach, as well as the dry approaches that we are going to refer to, with shell units and so forth. All of this, just to make sure, are absolutely properly done and can be properly done for tall buildings in seismic region. But there's a but. There is example from India, there are example from Japan, there are example here from New Zealand with cruciform joint. But if you're doing semi-precast, so if we are half precasting, half casting the connection, we are not exploiting the advantage of precast concrete. It has been mentioned very clearly, if you want to go fast and quick, if you want to have a full control of the quality of the manufacturing, you want to do all the job in the yard, all the job on your desktop, on your computer, and the construction should be as simple as. It should be complicated from the point of view of tallness, could be complicated from the point of view of speed of erection with dry elements, but you don't want to increase the complexity of the connection as you're typically doing with semi-precasting. So what I just showed to you can be absolutely, it is absolutely usable for tall buildings in seismic region, but we are going to a new era. The new era is saying that in seismic area, we don't want to have damage. We want to have life safety, but we don't want to have damage. We want to have a damage control. How can you get ductility without having damage? And an example of the good old way is this 22-story building. PwC PricewaterhouseCoopers is a 22-story building using a demolition of casting place approach in New Zealand. It got hit by the earthquake in 2010-11, specifically the February 22nd of February 2011, and it showed an amazing plastic hinge, the best ever seen plastic hinge in a beam. The joint, the column is well protected by capacity design, so you are going to have a weakest link of the chain in the beam, but we don't know how to repair it. In a way, I just gave a presentation in the Senate, in the Italian Senate, explaining what does it mean, the next generation of seismic protection, and explain that what you see here in terms of plastic hinge in a beam is what you see in a car, is exactly what we are accepting or expecting from a car, to plasticize itself to protect the pilot, to provide life safety. So the building do deliver life safety using an emulative connection, does deliver life safety by plasticizing the beams against versus the column, but at the end of the day, we don't know how to repair it. So a big issue is in terms of resilience, in terms of community resilience, in terms of sustainability of a city, is becoming, and that's the picture of the Christchurch, the city in New Zealand, which was hit by this sequence of events in 2010-11, and the reconstruction of the city had to become safer and, let's say, more resilient. Number of fatalities, 185, a lot. As been said, that could have been worse, could have been thousands. But the cost, 25% of the GDP, gross domestic product, was the cost of the direct repairing of the building itself, without even considering the downtime and everything else. So our emulative approach will deliver a beautiful skeleton which will have a plastic hinge which cannot be repaired, will deliver a frame system which is going to push the floor. The floor is not going to be rigid because we decide that. The floor is going to be pushed by the plastic hinge and is going to be damaged. All the non-structural elements are going to be compromised regardless of the structural skeleton, and precast facade can kill. So that's what we deliver so far today with the seismic resistance system coming from the code practice. Be careful, is the minimum by law, is not the target. So we want to do better, and if we want to do better, let's go and see what has been done in the past. We go back to the ancients, and they had earthquakes before we invented earthquakes. So they knew what was coming, or better, they knew that it was coming, they had to find a way, and one of the way that they found was rocking, was putting marble, precast concrete, if you wish, unreinforced precast concrete, beautiful blocks on the top of each other. And what they do, in the Greek way, in the modern Fori Romani way, just nearby where I am, and I have behind me an example of that sort of a seismic resistance system, which is the Colosseum. This is the ancient Agora temple, the Doric temple in Athens, in the below Agora, so not the top Acropolis. And the way to solve the problem of seismic resistance was to rock. So here it is, 2,500 years later, a new way to take seismic resistance into account in achieving low damage instead of only life safety. We have to go back to the 1990s. So from 2,500 years ago, we go back to only 25 years ago, 24 years ago, and we get to the PRESS program, Precast Seismic Structural System in the United States, which PCI, also endorsing this bulletin, has been basically the courage to invest on a new technology to try to go properly high in a seismic region. And Nigel Priestley, Professor Nigel Priestley, that Priestley of Park and Pauly, the capacity design gurus in New Zealand, was the chairman of that research program, which delivered at the end a 5-story building test, which could not be damaged in the form of precast frames as well as precast walls. So what you have seen so far in terms of stitching horizontally, stitching vertically, can be done with proper grouted sleeves or dissipator type of connection in between the precast elements. It's all about deciding the size. It's all about choosing what type of lateral resistance or stiffness you want to have. At the end of the day, you deliver a dry, ductile connection using post-tensioning horizontally, unbonded post-tensioning, so that you have a spring back, and using vertical post-tensioning between walls. So think about all your examples of the tall buildings that you've seen. You could have different type of connection vertically and horizontally, which could partially or totally use post-tensioning. What is the result? Instead of getting that plastic hinge by moving back and forth and creating damage, as in the car, you need to create damage to protect the pilots. You're going to just rock as the old temples was doing. And this rocking is controlled by a post-tension tie. So you're not able to go out of plane or, let's say, collapse by large deformation, by P-delta effects, but you're going to be picked up or kept in place by the post-tension, and you're going to dissipate. So it's a different way. In the 1950s, we were unfortunately seeing, in the 1950 construction, we were unfortunately thinking that a soft story was the inevitable way of behaving in an earthquake. We are still having, that's why I got stuck, we are still having plenty of these buildings which in the future earthquakes are going to behave like that. So let's call it the pre-70. Post-capacity design, the new way of doing was to save the building, so protect, save the people. life safety, save the people and protect the people, but not yet saving the building. And now the new way is to protect also the building, so our investments. We have been developing a lot of this type of technology in the form of rocking with internal rebars, as you would be doing it with a grouted type of sleeves, with an injection of mortar, or by moving out in a sort of a external replaceable dissipator, we call them plug and play, moving out the reinforcements, such that after an earthquake, you can actually go and check how they are and try as much as possible to replace them if need be, and go for the next aftershock. So we are moving into a completely different, as I said, era. In the new generation of buildings, we want to have a structural scheme as well as a facade, as well as the no structure element fully protected. And just to show you how does it work, the new Greek temple, this is an example of a shaking table that we did in Canterbury almost 10 years ago. Tell me if you're able to see. I don't know if you're able to hear. Can you hear it? Can some of my colleagues confirm?
Yes, Stefano. It's okay.
Thank you. Can you hear it?
Yes.
Okay, excellent. So post-tensioning, just imagine, go for the height. Columns all the way up, beams post-tensioning. Columns all the way up, beams post-tensioning. So basically you can go as tall as you wish, and I will show you some example of feasibility study that we've done. But the best example is definitely...
Sorry?
The best example is the 39-story building in San Francisco, which is not using as yet, was not using as yet the plug and play. The rocking of the temple. It's the new marble, if you wish, new reinforced concrete blocks, which is, instead of forming a plastic hinge, is actually rocking back and forth. So it's a much easier way to behave in a deformation, seismic deformation or seismic response without producing damage. You have a prime jointed ductile connection, which is leading to, we can't say damage, low damage. When you go to the end, there you are. And there are ways of producing facades with detailing. The precast facades are themselves heavy, obviously. People think that they are dangerous. It's about the detailing. Look at the connection over here. There is something behind which is allowing the movement. You're going to have, the movement. So basically, the more you move, the less you move. So there are very important ways to make seismic design of precast concrete tall buildings as safe as, literally as safe as. And this is one of the connection detailing where we're using U-shaped flexural plates underneath. This is underneath the beam. You see the facades are relatively moving towards the beam versus when compared to the beam. And so in this relative movement, think about your skin, you're able to move your skin, but you're not breaking anything between the skin itself and the skeleton. And that's what we are able to deliver today.
Stefano, just a word there, we can't actually see the video. Well, we can see the video, but it's not moving.
Oh, and before you were able to see the video?
Yeah, we can see the video itself, but it's static.
Okay. Sorry for that. We need to do it in a different way. I go to the end and maybe we're using during the question time. Now, I told you that I would have liked to give you a roadmap. Where can you find design code or guidelines about this type of approach? You go back to the FIB Bulletin 27. We are in 2004, and it's a joint venture in terms of chairmanship between Robert Park, Bob Park, and Fumio Watanabe-sensei from Japan, with an international committee I had the pleasure to be part of and to contribute to this specifically to the chapter of the jointed ductile connection. Then you can find a design handbook produced in New Zealand as part of the New Zealand Concrete Society endeavor to try to develop a new building system. You can apply the same displacement-based design for tall buildings with all the connection. And then FIB has pushed a lot, starting from the 78 bulletin I mentioned. So Spiros Tsukantas chairing the committee with detailing precast concrete buildings in seismic areas, practical aspects. And then the one that you've seen, which we're presenting over here, led by George Jones, precast concrete in tall buildings, where We are not showing the full design approach, but we are showing that techniques and technology can be used. Please refer to the Bulletin 27, 2000, or Bulletin 78, and so forth. Also, I'd like to mention the sustainability of precast concrete, which is still part of the Commission 6. David Fernandez, now Secretariat of the FIB, was chairing this committee, and now Albert de la Fuente from Barcelona is continuing the effort. And the idea is to show if and how precast concrete is, if well designed, can actually deliver sustainability. And I already mentioned to you, from theory to practice, 39-story building in San Francisco. Italy, we have buildings in Italy where if you are not in a seismic region, you can use the same Formula 1 technology to go for longer spans. So don't be worried if you're in Brazil, you can use this technology, I saw someone from Brazil, for longer spans. So you're just taking the power, instead of being power for lateral loading, is becoming power for gravity loading. Argentina, Costa Rica, New Zealand with exterior parallel plate. These buildings got hit by an earthquake. You see the vertical stitch, which in this case between rocking panels is actually made with a steel plate, which is going to plasticize and dissipate energy. It's a U-shaped flexural plate. This went through the earthquake in 2011, and there was basically no damage. So it went onto the media. People were saying how it could happen, how much it would have costed to make it happen. And I can tell you the answer is it cost less. New technology, properly designed, properly delivered, properly constructed, is going to be costing less than the traditional cast in situ wet connection way. So Christchurch 2050, the vision is to rebuild a city with new technology, and this new technology from concrete has been literally taken up by the timber industry. We developed the press lam, the pre-stressed laminated technology. It's been taken up also a little bit by the steel industry, but more importantly, there is a combination of materials, which is eventually what we could think about doing in the future. It's not only about going for precast concrete, although we are now having a seminar for FIB. We definitely want to promote the precast concrete because it's important. But think about a timber building, which is going to be happening no matter what, and is going to be missing power in the column. You're going to use precast concrete columns, which is exactly what we've been doing in this project. I'm pleased to show you just quickly a result of a European project, which we managed to be awarded, and working with a top team, including amongst everyone else, Arup from Amsterdam, Arup London, and we have a few people that are listening from here, Michele Palmieri, director in Amsterdam, associate actually, and Jonathan Ciurlanti, former PhD and at the University of Sapienza, and now structural engineering over there. Simona Bianchi from Delft now, Sapienza, postdoc, PhD postdoc, and now at University of Delft, working on multi-performance of this sort of a system. So think about the whole building system, and I'm going to show you the video and then it's done. You take a huge earthquake. It's a level of earthquake in New Zealand, which was the 22nd of February 2011, in the three directions. We managed to construct the taking building, which is using precast facades, precast columns, timber beams and timber walls, fiber curtains, gyps, fiber gyps, and glazing. We were not able to damage. The damage was minimal. I can't say there was no damage, but under an earthquake which was meant to collapse the building, we were able to repeat over and over the buildings. Few slides about the feasibility. We've been working for a few years. The first application of this feasibility study was with, I already mentioned the people, by Michele Palmieri. 2011, we published a paper about feasibility of tall buildings. We were looking at a building from Japan, Takenaka Corporation, a 40-story building. Now here we're looking at, with Jonathan Ciurlanti, Simona Bianchi, and Michele Palmieri, we're looking at an 18-story building in Groningen. So it's a redesign using this type of connection of a building which itself has a core wall and frames, so it's a dual system. And going right away to the dynamic response analysis, so the earthquake type of analysis, the red is the cast in situ or emulative. The green is the precast jointed ductile connection, and analytical, forget about that for the time being. Basically, you can deliver the same response from a movement point of view, acceleration, displacement, drifts. But the most important part is, at the end of the day, the recentering system, which with the potentially will come back. And so you will have no residual damage or residual deformation. In addition to, the plastic hinge will be forming using the car approach in the monolithic wet or wet emulative connection system, while in the rocking Greek temple, you don't have damage in the connection. So if we're looking at losses, this is a little bit of a complicated scheme, but look at the numbers, and I know that it's going to be recorded, so you will have the time to zoom and stay. The cost of repairing, which then means downtime, that means socio-economical issues of a low damage precast connection, which is going to cost you less to be constructed in a dry way, is going to be the cost of repairing at the downtime much, much less than an equivalent cast in situ wet connection type of building system. So there is basically a no-brainer. And if you specifically go also to look at not only the losses, but also the numbers of downtime, look at downtime. There are ways of doing it with the PACT software from the States. You can approximately calculate the reduction of downtime that you're going to receive, which means if you're using a low damage technology in precast, fully dry connections, you're able to get advantage, not only from the initial cost point of view, but also from the repairing cost and from the downtime. I'm done. I like always to show I do not have enough time just to show and mention the hundreds of people who have been working in the years about on this type of topics to raise the bar in seismic resilience, in seismic safety, and now in loss reduction to enhance the community behavior and resilience. And so I'm thanking all the people who have been part of that, and I'm thanking you for your attention. Grazie per l'attenzione, and kia ora from New Zealand, from down under New Zealand. George, back to you.
Thank you, Stefano. That was a very interesting talk. I think you will all agree. We have overrun a little bit, I see, but I'm sure you'll all agree it was worthwhile. We have a few questions. Let me just see what they are. From Kong Chandamuni, I have a question. Does FIB 101 Bulletin have a concept of how to model the joint of precast elements to analyze it in the software program? Maybe I can answer that. FIB 101 Bulletin is actually a state-of-the-art report. We discussed concept more so and what is developing out there rather than the analysis of the structure itself. I think Stefano touched on it in his talk, that it's more of a base for you to start from, and then you then go to further references from there. Stefano, would you like to add to that? Or?
Yes, I think I was expecting some of that. And so it's when I show the roadmap about FIB bulletins or the press design handbook, and you will find in them and in the references of them, all the detailing for macro modeling, fiber modeling of any beam column joint of any connection type, in any software.
Okay. There's a second question from Vladislav Shegkovstov. Hope I've pronounced that correctly. Thank you for a presentation. The weakest and the most important part in the building of prefabricated elements is their connection joints, especially welded joints. How is their implementation monitored during the construction progress and the condition throughout the life cycle of the building? Perhaps, Mischa, you would like to contribute to that one in reply?
If I can, I'll try, George. Well, from a construction perspective, I think what we try to do when connections are needed in buildings, and especially welded connections, is to take care of quality in all phases of the process. So it starts with the bit which is embedded in the element. That of course has standard quality control, looking at welds and bar lengths, all that sort of things. And then the way it's embedded in the element in the factory. There are normal quality control measures in place to assess that quality. And once it's on the building site and you are joining connections at the site, of course there's important things to take care of. Welding on site is always difficult and has implications around weather conditions, that sort of thing. So what we try to do is we always try to shelter those areas where welding is needed, and use available techniques to check the sizes of the welds and the quality of the welds by using ultrasound and that sort of thing. So typical normal quality testing systems can be used also for these elements. That's while under construction. During the lifetime of the building, to be honest, I'm not really aware of programs which check the welds or the connection integrity throughout the lifespan of the building. So I can't answer that part of the question for you.
Okay, thank you, Mischa. Pericles Maliosis, can you make some recommendations on how should the connections between the precast elements, especially in the vertical sense, mortar, wall shoes, starter bars, should be treated in the analysis stage, especially when the precast elements are not subject to full compression? Dick, maybe this is one for you.
Yeah. The short answer is no. We cannot make recommendations up to now. It depends highly on the type of connection you have, and there's also a FIP bulletin on precast concrete connections, and that provides a lot of different the different connections, but also the behavior of the connections. And the structural engineer should take select a connection, but also he has to make a judgment on the structural behavior of such a connection, and is responsible for how to implement it into his structural model, I think.
Yeah, no, I think that's right. I think the connection should, in effect, take account of the analysis as well. One follows the other, in that if you've got a hinge connection, then, a hinge connection in the model, then the precast connection, should reflect that. Maybe it's just transferring shear rather than taking any bending moment. Fourth question, T and Bosman. Thanks to all the speakers for excellent presentations. My question, how is the global stiffness of a tall building affected when considering the use of seismic resistant ductile connections? Stefano, that's probably your expertise.
Thanks for the question. First of all, let's go back to the basics of what is the post-tension ductile connection. You have the post-tensioning capable to provide you with basically full uncracked stiffness at the beginning. So until you get to the decompression point, you have a higher stiffness in a post-tension connection than in a cast in situ connection, which is going to be cracking much earlier, and you have to use a crack stiffness as early as. So given the comparison between the two systems, now the question is much more general. So is the global stiffness affected by, depends on the structural system, how many columns, how many beams are coupling, if the structural system is a wall or is a frame, if it's a wall and a frame together. So the global lateral stiffness is going to be dictated by the structural concept. The local stiffness of the connection is going to be higher, at least, than, or in the initial stage as high as, and then higher when you crack the concrete and you don't crack the post-tension concrete in one solution versus the other. So you have the benefit of it.
One question here, Stefano, probably again for you. Are there certain building height limits based on beam column connection types?
Good question, and the answer is there's no answer, for the same reason for which we're talking about tall buildings. It's a matter of conceptual design. We do know that it's unlikely that the taller you get, the more you're able to use frames. So in terms of structural concept or conceptual design of the structural lateral resisting system, we do know already that frames alone can lead to a certain range of height. And then you do need to use dual system, walls and frames, or walls alone, or walls and outriggers. So these are the basics of tallness in terms of seismic, in terms of design, and in seismic becomes very similar. So in principle, there is no limit in terms of beam column connection type in terms of height, because it depends on how slender the building is. You can be as tall as and as large as, so you're squat, and so in principle you can use frames alone all the time. But let me say in a different way. If you're using a dual system, frames and the one that I was showing at the end, column, core walls, and outrigger or outer frames, the beam column connection can go as high as the core walls can make it. And I say core walls because maybe it's more than one. Tube on tube and everything else. So it's a conceptual design issue.
Okay. Thank you again, Stefano. That's all the questions I can see for now. So thank you to all the presenters for very interesting presentations, and thank you to all the participants for logging in and listening to this webinar. Thank you very much.